Hello, everyone. My name is Tom Rositz, and I'm the Vice President, Director of Engineering for Ohio Concrete. Also with me is Mark Pardee, Field Engineer and Ohio's ACPA Representative for Ohio Concrete. We welcome you to today's webinar, Hot Weather Concreting in Ohio, where we will discuss the effects, mixture and placement adjustments, as well as tips for hot weather concreting. This is our standard disclaimer used for our webinar programs. We are using and citing sources that are applicable to the subject matter. Note, however, that there are limitations and judgments that need to be applied when using information presented in this program. The presentation will discuss the hot weather impacts for the producer, contractor, and tester, which is going to cover defining what the definition of hot weather concreting is, the effects on hot temperatures or high temperatures on concrete, cooling concrete methods and mix design adjustments, project planning and best practices, finishing problems and things such as plastic shrinkage cracking and drying shrinkage cracks, as well as curing and protection, reduction of concrete strengths, and testing procedures. Ohio Concrete has a series of technical tips, one of which is titled Technical Tip Number 10, Hot Weather Concreting. This is available to our members. Another Ohio Concrete resource available online at Ohio Concrete's website is the Industry Recommendation for Exterior Concrete Flatwork. We also have another program that we had done earlier this year that discusses scaling, and this has a direct connection to this program as well with hot weather concreting. Let's start with the how, when, and why hot weather is defined in contract documents. The first place to look is the project specifications, as this is the contract document which includes the requirements of the work. Often, concrete industry codes are referenced in contract documents, such as the ACI or American Concrete Institute codes 318 as well as 301. There are hot weather provisions that are defined that further reference ACI 305.1, which is the specification for hot weather concreting. I'll now turn this over to Mark, where he will review ACI 305.1, which is the specification, as well as the report that further details hot weather concreting. Take it away, Mark.
Okay, thank you, Tom, and good morning to everyone. We'll be looking at ACI 305.1-14. This is the specification for hot weather concreting, and especially sections 1 and 3. Section 1, general, includes a definition of hot weather concreting and submittal requirements. Note there is a requirement for a pre-placement conference 15 days prior to beginning concrete construction to review hot weather concreting properties. Attendance at this meeting shall include contractor representatives, subcontractor, testing agency, pumping contractor, the engineer of record, and the ready-mix producer. Per ACI, the definition of hot weather concreting is conditions that impact the quality of fresh concrete or hardened concrete by accelerating the rate of moisture loss and the rate of cement hydration, or essentially conditions with high ambient temperatures, high concrete temperature, low relative humidity, high wind speed, and solar radiation. In Section 3, Execution, ACI describes preparations, such as dampening the subsurface before concrete is placed, prevent evaporation from the concrete surface by monitoring the site conditions. They are air temperature, relative humidity, wind speed, and temperature of fresh concrete at time of discharge. The maximum temperature of fresh concrete at the time of placement is 95 degrees. And this maximum of 95 has been adopted by ODOT specifications. The request for a maximum fresh concrete temperature exceeding 95 must be supported by pre-construction testing, shall require materials similar to those proposed for the use on the project and under similar conditions. Concrete production methods to reduce concrete temperatures include cooling the aggregate stockpiles, chilling the mixed water, and in some extreme cases using liquid nitrogen. Reference is made to ACI 308 Guide to Curing to control surface bleed water evaporation, and the curing requirements of standard test specimens for acceptance for ASTM C31, and protecting the concrete surface from rapid temperature decreases to avoid thermal shrinkage cracks. When the rate of evaporation of the bleed water exceeds 0.2 pounds per square foot per hour, precautionary measures such as windscreens or fogging are recommended. Use the nomograph to estimate the surface evaporation rate. Enter with the air temperature, 85 degrees, move up to the relative humidity at 20%, and continue clockwise. Move right to the concrete temperature, 80 degrees, and down to the wind speed at 10 degrees. Now move left and read the approximate evaporation rate. With some concrete mixtures, such as those containing certain pozzolans, cracking is possible even if the evaporation rate exceeds 0.1 pound per square foot per hour. Concrete containing silica fume is particularly prone to plastic shrinkage cracks because of a lack of bleed water. Cracking can develop with evaporation rates as low as 0.05 pounds per square foot per hour. A professional environmental meter allows one to measure the instantaneous evaporation rate rather than going by weather data from nearby stations. For example, wind gusts at a specific job site location may play a significant factor in the evaporation rate calculation. Data logs can be transferred to a mobile device wirelessly or to a computer. This model has the ACPA evaporation rate nomograph built in and displays the evaporation rate on the screen with no calculations required by the user. Another important document is ACI 301R-10 Guide to Hot Weather Concreting. This report provides a detail on potential problems and practices, effects of hot weather on concrete properties, production and delivery, placing and curing, testing and inspection. The appendix includes methods for cooling the fresh concrete. Potential problems in hot weather. In the fresh concrete, there is an increased water demand, an increased rate of slump loss, an increased rate of setting, increased tendency for plastic shrinkage and thermal cracking, difficulty in controlling air entrainment, and reduced abrasion resistance. In the hardened concrete, there can be a decrease in strength, decrease in durability, resulting from additional water, increased permeability, increased tendency for drying shrinkage, and differential thermal cracking, decreased durability from cracking, and variable surface appearances such as color differences or cold joints. Higher temperatures accelerates formation of cement bonds, but it reduces the quality of those bonds. These microscopic views depict different degrees of cement hydration. 1 shows particles of unhydrated cement, 2 is partially hydrated cement, and 3 is a single particle fully hydrated. Proper curing procedures ensure that sufficient water is available for the degree of hydration necessary to achieve the desired concrete properties. This graph shows the effect of high initial concrete temperature on compressive strength. The concrete with the lowest one-day strength, shown in red, becomes the concrete with the highest 28-day and ultimate strength. If the water content had been increased to maintain the same slump, the reduction in strength may have been greater than that shown. The proper fabrication, curing, and testing of compression test specimens during hot weather is critical. Steps should be taken to assure ASTM C31 procedures are followed, specifically the initial curing strength for test specimens. Consider the batch water required to hold a 3-inch lump with increasing concrete temperatures. As concrete temperature increases, there is a loss in slump that often is compensated for by adding water to the concrete at the job site. At higher temperatures, a greater amount of water is required to hold the slump constant. As shown in this graph, if the temperature of freshly mixed concrete is increased from 50 degrees to 100 degrees, about 33 pounds of additional water is needed to maintain that same 3-inch slump. The addition of water results in a higher water-cement ratio, thereby lowering the strength at edges and adversely affecting other desirable properties in the hardened concrete. This is in addition to the adverse effect of strength at later ages due to the higher temperature, even without the addition of water. High temperatures in fresh concrete increases the rate of setting and shortens the length of time for which concrete can be transported, placed, and finished. As a general rule of thumb, the concrete set time changes about 33% for every 10-degree change in the initial concrete temperature. Different cements behave differently. Here, cement A is in blue and cement B is in gold. The chart shows that as concrete temperature increases from 73 to 90 degrees, the concrete set time is reduced by a half hour with cement A or by 2 hours with cement B. Air entrainment is also affected in hot weather. At elevated temperatures, an increased amount of air entraining admixture dosage is required to maintain a given air content. Concrete that contains the slower setting cements is more likely to exhibit plastic shrinkage cracking if not protected. The cement content shown should be kept as low as possible, but sufficient to meet strength and durability requirements. The inclusion of fly ash or slag cement should be considered to delay setting time and mitigate the temperature rise from heat of hydration. Water-reducing admixtures can offset increased water demand and strength loss that could result in higher concrete temperatures. The usual method of cooling concrete is to lower the temperature of the concrete ingredients before mixing. The aggregates have the most pronounced effect on concrete temperature because they represent 70 to 80% of the total mass. This graph shows the effect of aggregate in mixing water temperatures. For example, assume the initial concrete temperature is 88 degrees. The ingredients are cement at 150, aggregate at 80 degrees, and the water at 80 degrees. To drop the concrete temperature 1 degree, you could either reduce the aggregate temperature 1.6 degrees or reduce the mixed water temperature 3.9 degrees Fahrenheit. Methods of cooling fresh concrete include A, sprinkling water on the aggregate stockpiles, B, cool misting the drums, C, crushed ice charged into the truck mixer, and even D, liquid nitrogen being added directly into the central mix drum or the mixer drum. What about the mixer drum color? Lighter mixer surfaces such as white minimize solar heat gain, and that helps to reduce the concrete temperature. Based on a 1-hour delivery time on a hot, sunny day, concrete in a clean white mixer drum should be 2 to 3 degrees cooler than in a black or red mixer drum, and a ½ degree cooler than in a cream-colored drum. Another rule of thumb, in order to reduce the temperature of fresh concrete 1 degree, reduce the aggregate's temperature by 1.6 degrees, or water by 4 degrees, or cement by 9 degrees. The approximate concrete temperature can be quantified from the temperatures of its individual ingredients using this equation, where T is the temperature of the fresh mixed concrete, and the T's with subscripts are the temperatures of the individual materials, aggregates, cement, added mixing water, and free water on the aggregates. The M's represent the mass of these individual ingredients. Heat generated during cement hydration raises the temperature of the concrete to an extent that depends on the cement content. As a general rule, cement hydration temperature rises 5 to 15 degrees for every 100 pounds of cement. At 96 degrees, for example, cement is hydrating at 2 times the typical laboratory rate at 73 degrees and will cut the set times in half. Batch plant applications. Select materials in mixed proportions that have proven performance, such as lower cement contents and set retarding admixtures. Cool the concrete or one or more of its ingredients. Coarse aggregates will have the greatest impact. Use a concrete slump that allows rapid placement and consolidation, which likely requires a plasticizer. Add fibers to the concrete mix. Job site applications. Organize a pre-construction conference to discuss the precautions. Reduce the time of transport, placing, and finishing. Minimize waiting time. Don't allow trucks to sit on the job site. Schedule concrete placements to limit exposure to harsh atmospheric conditions. Consider nights or other dates. Consider methods to limit moisture loss during placing and finishing, such as sunshades, windscreens, fogging, or evaporation spraying. Apply temporary moisture retaining films to control evaporation after strike-off and prior to finishing. Schedule placements when walls and roof structures are in place. What is wet curing? Well, what is curing? First of all, it's the maintaining of an adequate moisture content and temperature in the concrete at early age so it can develop properties the mixture was designed to achieve. Don't let it dry out for at least 3 days. Apply curing immediately after finishing. And there is the greenhouse effect caused by plastic sheeting can result in visible discoloration streaks. Wet curing, however, is the most desirable type of curing, but not always practical. Plastic sheets with soaker hoses is a good option. White fabric covers keep the moisture in and reflect the solar heat. Use a white pigmented reflective compound where concrete will expose to the sun. Coverage should be thick enough so that it's not spotty. Apply curing compound immediately after finishing. Be sure to coat all exposed areas, including edges. The need for moisture curing is greatest during placement and the first few hours after finishing. Curing water should not be more than 20 degrees cooler than the concrete itself. Otherwise, cracking can result from thermal stresses due to temperature differentials between the concrete and the cure water. Continuous moisture curing for the entire curing period is preferred. However, if moisture curing cannot be continued beyond 24 hours, while the surfaces are still damp, the concrete should be protected from drying with curing paper, heat-reflecting plastic sheets, or membrane-forming curing compounds. If this is not practical, a curing compound should be applied immediately after final finishing to keep the concrete surface moist. Avoid repeated wetting and drying of the concrete surface. Crazing is a pattern of fine cracks, shown here, that do not penetrate much below the surface and is caused by minor surface shrinkage. To prevent crazing, start curing as soon as possible. How to minimize the risk of unanticipated cracks. Well, shrinkage is unavoidable. It's normal to experience drying shrinkage, cracking on every concrete slab. Concrete shrinks an 1/8 inch for every 20 feet approximately. All concrete shrinks. As concrete shrinks, it cracks. So we plan for this by using isolation joints and contraction joints to accommodate shrinkage as the concrete volume changes. A restraint mechanism that prevents the concrete from shrinking results in a crack. A random crack is merely one that occurs outside of the planned joint. In general, use concrete with a moderate slump not over 5 inches. Avoid retempering concrete to increase the slump before placement, as this will increase shrinkage. Start curing as soon as possible to prevent rapid drying shrinkage. Plastic shrinkage cracking is usually associated with hot weather concreting. However, it can occur anytime ambient conditions produce rapid evaporation of moisture from the concrete surface. Plastic shrinkage cracks sometimes occur in the surface of freshly mixed concrete soon after placement, during finishing, or shortly thereafter. These cracks occur when water evaporates from the surface faster than water can travel to the surface during the bleeding process. This condition creates rapid drying shrinkage and tensile stresses in the surface that often result in short, irregular cracks. The following conditions, individually or collectively, increase evaporation of surface moisture, with increasing the possibility of plastic shrinkage cracking. That is, high cementitious contents, low water-cement ratios, high concrete temperatures, high air temperatures, low humidity, and wind. How to minimize plastic shrinkage cracking. Provide proper equipment and manpower. Fogging and misting, or using evaporation retardants. Dampening the subgrade. Setting up wind barriers. Using synthetic fibers. And adjusting the set time to minimize plastic shrinkage cracking. And now I'm going to turn the program back over to Tom.
Thanks, Mark. As has been presented, temperature has a major effect on setting time of concrete. So concrete placed under elevated temperatures will set more rapidly and therefore need faster finishing. This also has a pronounced impact on strength. Where early strength of concrete is higher, but later, say 28-day strength results will not be as high as concrete cured at around 70 degrees Fahrenheit. So it's therefore critical that concrete placed during hot weather is cured as quickly as possible. Curing needs to be continuous and, as Mark had said, for at least 3 days. Covering the placement with water, wet burlap, plastic sheeting, or liquid membrane curing compound. The benefit of using a white pigmented compound not only allows an indication of the coverage, but it also reflects the heat from the surface, from the sunlight. Also, any test specimens that are cast need to be protected and stored under proper temperatures as required for ASTM C31. Let's go ahead and take a look at concrete specimens. For C31, ASTM C31, there are really two different purposes for casting field specimens. One test is to determine the strength potential for the concrete as it's been delivered to the job site, and the other is for determining the strength of the concrete in place at a given time. Both tests are covered, as I said, under C31, and the one big difference between the two test procedures is the method of curing required for these specimens. Because correct cylinder curing is commonly neglected, invalid test results are often misinterpreted as test failures. So let's take a look first at the standard cured specimens. The first purpose of the cylinder testing is really to confirm that it meets the project specifications for strength. That is, concrete that is delivered to the job site will meet the design strength, which is typically at 28 days. So this procedure requires that those specimens that are cast remain on the job site for the first at least 24 hours, typically move no longer than 48 hours, and they're stored in a temperature environment between 60 and 80 degrees Fahrenheit when the concrete strength is less than 6,000 psi, or at a higher temperature, 68 to 78 degrees Fahrenheit, for strengths either equal or greater than 6,000 psi. But again, the key here is that we're keeping those specimens in that set environment. And then within 16 to 24 hours, the cylinders, or certainly no longer than 48 hours, they're removed from the job site, taken back to typically the lab, where they're demolded and stored in a moist condition, in a moist cure room or a cattle tank of lime water, in a temperature of 73 degrees Fahrenheit in a very standardized method. Now, field cured specimens are for a different purpose. This is to confirm that the concrete that has been cast on the project site is strong enough for the next step to occur on the project, whether that is putting the concrete into service, whether contractors can start traveling equipment on it, or really getting to the next sequence of their construction cycle. So these cylinders, they are protected in or near as possible to the concrete as placed. The molds are then removed at the time the forms are removed. So really, we're trying to duplicate the concrete specimens being under the same condition or nearly the same condition as the concrete that's placed at the job site. So two very distinct reasons on why we are casting specimens. So let's recap some of the items that we've covered on hot weather concreting. Warm, moist conditions are actually ideal for durable, strong concrete. So we want to enhance and create hydration of the cement. However, when we get into conditions of hot, dry, windy conditions, they can create problems. And as we've detailed, some of the solutions include cooling that ingredients that make up the mix, using mixes that have been adapted for high temperatures. Those include using supplementary cementitious materials such as fly ash or slag cement, or using retarders, liquid retarders. The consistency also needs to allow for rapid placement and consolidation. Transport, placement, consolidation, and finishing with the least amount of delay. Maybe trying to reduce the exposure during hot weather, maybe starting early in the morning or placing at night. Very common for the bridge decks here in Ohio. Protect this placement from moisture loss at all times during placement and curing. So this includes fog sprays and evaporation retardants. So some of the conclusions: placing, finishing, and curing of concrete is not an exact science. There needs to be adjustments for the placement. We understand that the contractor is at the mercy of the weather, and every day is essentially different. Therefore, concrete mixtures as well as the placement procedures will need to be modified for that particular day's placement. Curing is essential to quality concrete. And sometimes we need to apply intermediate curing, which is done with either fog mist or evaporation retardants during the placement, so we don't allow that top surface to dry out. And then placing final curing as soon as possible after all finishing is done. Also, specimens that are cast or job site acceptance need to be placed under the conditions of ASTM C31. The perfect day to place concrete is 70 degrees Fahrenheit, 100% humidity, and no wind. Well, we don't have many of those days in Ohio. So we do need to make exceptions, and we do have to make modifications. So consider this: if you are hot and sticky with perspiration, that it's typically a good day for concrete. However, if you're working outside and you've got your sunglasses on and there's a nice breeze, and that might be a clue that rapid surface evaporation is taking place and that precautions need to take place. Provided are some of the slides. In the slides, we used some industry sources such as American Concrete Institute, National Ready Mix Concrete Association, FHWA, Portland Cement Association, and those which we've created here in-house at Ohio Concrete. There's also a really good article that Ken Hover placed in a structures magazine called Keeping Concrete Cool in Heat of Summer. That concludes our hot weather presentation. We've reached our half an hour, and we can now open this up to questions. So with that, let's please direct any questions into that box that you see on your screen. We've got one that has come in, so I'll go ahead and see if Mark could answer this. How can you distinguish between plastic shrinkage cracks and drying shrinkage cracks?
Okay, Tom, I'll take a stab at this. It's a good question here, and generally you can tell the difference between plastic shrinkage cracking because they're very shallow cracks, usually a little shorter in length, and they appear before, during, or immediately after your finishing process. They're typically parallel to each other and perpendicular to the wind direction. The drying shrinkage cracks usually appear a little later in the process, and they can be deeper and wider and can extend a network all the way across your panel or your slab.
Thanks, Mark.
One other question here that's come up, Tom, I'll throw it back to you then. Says here, since many of today's concrete mixtures use fly ash or slag cement that which retard the set time, would liquid admixture retarders be recommended as well?
Good question. There does need to be some caution with mixtures that are blending cementitious powders and liquid retarders together, since the concern is that they may over-retard the mix and increase the potential for plastic shrinkage cracks. Understand that liquid admixtures are really used to offset the accelerating of the set during hot weather. So when you've got a retarded mix, that top surface of the concrete, especially for flat work, is exposed to hot, dry, windy conditions. And it may not be ready yet for final finishing. So it does need to be protected, kept moist, again, using fog misting or evaporation retardants.
Okay, thank you, Tom. We have another question that's been sent in here, and it reads, should joint spacing be adjusted in hot weather due to additional shrinkage? Okay, I'll go ahead and take this one. Joint spacing recommendations are in ACI and different documents, and they generally give you a range. So extending the joint spacing out further assumes more risk than closer joint spacing. So I like this question because typically when we make joint spacing recommendations, we like to move them a little closer, and certainly that would help. However, I don't think this would help with plastic shrinkage cracking, as those develop before you even get to the point where you're saw cutting. And I think in hot weather, you should try to install the saw cuts earlier and sooner in the process, maybe with an early entry saw, to help relieve that problem of early cracking.
Okay, Mark. Here's another question that came in. What is the best time to apply evaporation retarders? And I'm assuming the question is regarding the sprays that are applied on top of the surfaces, typically for flat work, as the body of the concrete is still setting and the top is exposed. So it's a good question. And this is kind of one of those things that need to be done really as a timing when the surface moisture has that sheen has essentially gone away. And maybe there is also now a color differential on that top surface where it's starting to lighten up from the darker surface. There really isn't a risk of putting it on too soon. The bigger risk becomes trying to finish any of that material into the surface because it is 9 parts water. So they are called finishing aids. Another term, I don't really care for that term, but it does aid the finisher, but they're not meant to be finished into the concrete because of the amount of water that makes up that evaporation retardant. They're meant to lay there on top of the surface and then surface dry. Well,
okay.
That kind of concludes the questions. And again, look for upcoming webinars. We've got another one that we're planning for October. And if there's any suggested topics that you would like us to also discuss, please send those in to us. Thank you for today's time, and we appreciate everyone's participation. Thanks.
Thank you.